Good morning and welcome to this presentation entitled The Impact of Learning Factories on Teaching Lean Principles in an Assembly Environment. My name is Fabio Monetti and I co-authored this work with Eleonora Boffa, Dr. Andrea de Giorgio, under the supervision of Professor Antonio Maffei at KTH Royal Institute of Technology in Stockholm, Sweden. The content of this presentation is as follows. First, we state the motivation behind this work, introduce the topic and provide some context, describing what learning factories are and the principles of lean manufacturing. Then, we will present the laboratory we built at KTH and how we developed an experimental setup for this work. After that, we will present the data we collected and how we analyzed them, and show the results, followed by a discussion on the implications of our findings. We will conclude the presentation with some final remarks and an outlook on future developments for this work. Traditional teaching methods do not provide the desired improvement in the acquisition of knowledge and development of the skills necessary to apply lean manufacturing principles. Employing learning by doing methods facilitates the acquisition of concepts related to lean manufacturing and the development of such skills. That is why in recent years several academic institutes and companies have promoted the construction of learning factories facilities. From a pedagogical perspective, this means that courses and training programs that include a learning factory approach aim at fulfilling higher educational objectives than regular lectures. Looking at the Bloom's taxonomy model for the cognitive domain, the learning factory, through the learning by doing approach, allows us to step from basic cognitive objectives, such as remembering or understanding, to more complex ones, like applying and analyzing. The term learning factory identifies a system that integrates elements of education in a realistic production environment, implementing the factory-to-classroom concept. The learning factory creates the suitable conditions for students to practically engage in different situations by applying the concepts and the tools presented in class. The teaching-learning process is then moved closer to real manufacturing problems through emulation of a simplified shop floor, giving the opportunity to students to engage in hands-on activities. These help students in actively engaging in a practical task, observing, reflecting, and discussing the activity with their peers, generalizing the events and suggesting improvements, and putting knowledge into practice for better information retention. For engineering students, the learning process requires experience to absorb complex concepts from classroom education. This makes the learning factory a suitable learning activity to be embedded in engineering programs. On the other hand, lean manufacturing refers to a philosophy that it is intended to reduce waste or non-value-added activities in the entire product's value stream, while promoting continuous improvement, using specific tools like the ones in the figure. Such philosophy lies on 5 basic principles: identifying the value from customer's perspective, mapping the value stream to include only value-adding processes, creating continuous flow, establishing a pull system, and striving for perfection by continuously improve the company's processes. In view of what just mentioned, learning factories appear to be a suitable teaching and learning activity for lean manufacturing education and training of engineers. So, the work hereby presented analyzes the impact of such learning factories on the student's learning process when teaching the learning manufacturing concepts in an assembly environment. The Lean Lab, developed at the Royal Institute of Technology in Stockholm, is taken as a case study for our work. The laboratory simulates a realistic manufacturing environment whose main goal is to involve the students to develop solutions, applying appropriate lean tools such as 5S and Kanban. The Lean Manufacturing Lab consists of an assembly line with 6 workstations, where the students learn how to assemble a small and easy product. The assembled product has a simple template structure composed of several blocks and labels that differ from each other, thus requiring the operators to change tools between the operations, as you can see in the video, which represents a partial set of instructions. For example, in one of the stations, the student should fasten the banner screws with one screwdriver and then the roof screws with a different one. The activity is structured in 3 rounds, each of them lasting 12 minutes. The rounds are designed to show a stepwise improvement of the line, applying lean manufacturing tools. The first round is set in a disorganized way to highlight the waste in the whole assembly process. At the end of this round, the students engage in a group discussion that is aimed at identifying problems and suggesting relevant lean tools to solve them. The second round starts with the students implementing the suggested LM tools, and then it is run with the proposed improvements in place. Another group discussion raises then the problems that are still occurring, and additional tools are evaluated and suggested for implementation in the third round. This last round consists of major improvements to the previous setup, for example, a reduced number of stations, use of conveyor belt, and so on. A single product consists of the sum of the times for said product to be assembled at each station, 1 to 6. We call this line throughput time. The throughput time of the product for every iteration of the Lean lab is recorded, even the ones that exceed the 12 minutes mark. We give additional time to complete the assembly, but we label these cycles as overdue. The table shows how many products the students complete in each round and how many of them are on time, along with the percentage of on-time completion. Then we check the 3 rounds assembly time populations for normality by looking at the normal probability plot, which is not displayed here, and performing a Shapiro-Wilk test. The test do not show evidence of non-normality for round 1 and round 3, but it highlights that round 2 is significantly non-normal. We also plot a box plot with the 3 populations to have a first insight into how far apart and different they look. The 3 populations, which represent the line throughput time in 3 rounds, are quite distant from one another, and also they seem to have unequal variances. Then we test separately round 1 against round 2 and round 2 against round 3 to check if the differences are statistically significant using a t-test with 2 samples and unequal variances. We want to check if there is evidence that applying the lean tools through the rounds of the lab helps reducing the throughput time for the product. Since strong indications of non-normality should not be ignored and the performance of the t-test can be affected, we choose to also perform a non-parametric Mann-Whitney U-test on the same hypothesis. The line throughput times recorded during the first round of the lab compared to the times recorded during the second round demonstrate to be significantly higher. Likewise for the times of the second round compared to the times of the third. The Whitney U-test is generally less powerful than its parametric equivalent, but its value is not hindered by non-normality. Thus, a positive result might confirm the implications of the t-test. T-test and the Mann-Whitney U-test results are the same, so we can conclude that both are reliable with a strong power. Given the box plot information and these results, we can confirm that the time for assembling a complete product with the setup from round 1 is significantly higher than with the setup from round 2, and consequently that the setup of round 3 makes the operation significantly quicker than round 2. After the students complete all the rounds of the laboratory, we submit a questionnaire to collect their opinions about the experience as a whole and its usefulness to understand and learn the lean manufacturing principles. The course has a total of 88 enrolled students who do the lean lab activity. Since not all the students that take part in the lab participate in the questionnaire, we need to calculate the margin of error E, or confidence interval, for the answers, using the inverse equation for calculating a significant sample size. We use the adjusted sample size N0 because our population is small, so a finite population correction is applied. Since only 25 students out of the 88 enrolled in the laboratory activity participated in the submitted questionnaire, we calculate a margin of error of 16.68. The figures here show the answers to the questionnaire. The students found the lean lab experience to be useful and satisfactory, and that it helps in learning the LM principles. After collecting the responses, we conducted a chi-square test to examine the significance of the students' picks in the questionnaire. The majority passed the test with p-value lower than 0.05, except 2 questions, 3.4 and 3.6, as highlighted in the figure. Results for the throughput time show an increase in the number of assemblies that are completed within the 12-minute mark, and the average throughput time decreases, with round 3 averaging results almost 4 times less than round 1. This means that the lean manufacturing tools serve their purpose of easing the operator's jobs and making an assembly line as lean as possible, enhancing the productivity. Given the valuable experience of the lean manufacturing lab, the students increased their level of educational objectives in the cognitive hierarchy of Bloom's taxonomy. From just a knowledge and comprehension level that comes from learning in the classroom, they go to an application and even analysis level, which gives them potential to become better learners and better professionals. The answers from the submitted questionnaire confirmed that our students appreciate the hands-on experience and that they are very satisfied with the activity. We also think that the lab is useful to improve the learning process. Thus, including more similar activities in other courses could be a useful teaching approach. As a next step, future work includes collecting more data from future iteration of the course to analyze a wider sample of the population, to reduce the confidence interval and better capture the significance of the student's experience, and to compare the results over the years. Moreover, the participation to the questionnaire will be made mandatory for all students taking part in the course. Thank you for listening. This is the end of the presentation.